The stars that never got worlds. Why do some stars never get worlds? There are few questions that cut more deeply into our place in the universe than this one. If planets form naturally around young stars, as our best models say they should, why do we keep finding lonely stars with no detectable planets at all? Are we looking in the wrong way? Or are there truly stars that shine for billions of years without a single world in orbit, without a single chance for life to begin? We only have to look at our own backyard to feel how strange that is. Our solar system is busy, crowded, almost chaotic. Giant planets circling far out, rocky planets tucked close in. Asteroids, comets, dwarf planets, moons. It is a full dynamic system. But while we are used to this cosmic bustle, imagine a different scene. A star, very much like the sun, burning quietly in the dark. No planets to catch its light, no moons to cast shadows, just a bare star rising and setting over nothing. In the hunt for alien life, that kind of emptiness is unsettling. Did that star simply never get a chance to build planets? Or, even more disturbing, did it build them and then lose them? This is not just a poetic image. Surveys from Kepler and TESS show us that planets are common, especially small, Earth-like, and Neptune-sized worlds. But while many stars host rich planetary systems, others appear stubbornly empty. Two stars can be born in the same collapsing cloud at the same time, with almost the same mass. And yet, one ends up with a complex system while its sibling seems bare. So it's time to find out the truth. This is not random luck. It should be noted that young stars almost always begin with swirling disks of gas and dust. We see them directly. ALMA has photographed them as bright rings and dark gaps, places where planets are thought to be carving paths. JWEST is now taking this further, watching baby stars and their disks in infrared detail, almost like time-lapse footage of planetary systems under construction. But here's the twist. Many of those disks are too light, too short-lived, or too violently disturbed by radiation and companion stars to ever assemble full planetary systems. This means some stars never graduate from dusty halos to real planets. Others may form a few small worlds, but lose them to gravitational chaos or intense stellar storms. So, let's begin with a promise. By the end of this video, we will be able to look at almost any type of star, from tiny red dwarf to sun-like giant, and make an educated guess about its chances of having planets at all. Optimistically speaking, we might even see where our own sun sits in this cosmic lottery, and how lucky we really are. Why this question decides how crowded the universe is, but why does this cosmic lottery matter so much? If we want to know how crowded the universe really is, this is the question that quietly controls everything. In the hunt for alien life, astronomers often turn to something called the Drake equation. It is basically a chain of guesses, each one multiplying the next. How many stars form, how many of those stars get planets, how many of those planets are in the Goldilocks zone, and so on, all the way to intelligent civilizations. This means that if a large fraction of stars never get planets at all, the whole product collapses. Even if life is common on the right kind of planet, there might simply not be enough planets to work with. For a long time, though, many astronomers quietly assumed the opposite. Because we had not detected any planets around other stars, it was easy to imagine that our own solar system was rare, maybe even unique. But while we stared at the sky and saw only bare stars, the limitation was not the planets, it was our instruments. Then surveys like Kepler arrived, and everything changed almost overnight. By staring at over 100,000 stars and watching for tiny dips in brightness as planets cross in front, Kepler revealed that small, Earth-like and mini-Neptune worlds are everywhere. Around red dwarf stars, especially, tightly packed systems of planets orbit so close and that a year can last only a few days. Optimistically speaking, it looked as if almost every star might host at least one world. But there was a catch. Kepler, TESS, and most of our methods are biased. We are best at finding big planets, close to their star, on orbits that pass exactly between us and the star. A system full of small, distant planets can look completely empty in our data. It should be noted that even after correcting for those biases with careful statistics, some stars still appear truly barren, with no sign of planets down to very small sizes. So where did their worlds go, or were they never there? To answer that, we have to rewind the clock. We need to watch stars being born inside cold, collapsing molecular clouds, wrapped in swirling protoplanetary disks of gas and dust. In those first 3 to 5 million years, the entire future of any planetary system is decided. If the disk is massive enough, cool enough, and long-lived enough, it can build a rich architecture of planets. If not, the window slams shut. ALMA and now JWEST show that most young stars do have disks, but not all disks are equal. Some are heavy and wide, easily capable of forming multiple Earth-like planets. Others are thin, quickly shredded by stellar radiation, magnetic winds, or even a nearby companion star that truncates the disk. Two stars can be born in the same cloud, yet one ends up like TRAPPIST-1, while its sibling is left with nothing. So it is time to find out the truth. In the next section, we will follow that journey from cloud to disk to planets, and see exactly where some stars lose their chance at worlds, and perhaps at life itself. From cosmic cloud to planet factory, where odds are set so if some stars lose their chance at planets, where do those chances first appear? They begin long before any planet orbits a shining star, inside a giant, cold molecular cloud. Picture a vast, dark region of gas and dust, light years across, colder than Pluto's night side. Gravity tugs on slightly denser pockets, and those patches start to collapse. But while gravity pulls inward, turbulence and rotation keep everything from falling straight to the center. The cloud fragments into many dense cores, each one a tiny embryo of a future star system in the making. As one of these cores contracts, something crucial happens. Conservation of angular momentum takes over. If the core spins even a little at the start, that spin cannot just disappear. So the collapsing material flattens into a thin, rotating disk around a newborn star. This is not a cosmetic detail, this is the planet factory. That protoplanetary disk is the only raw material planets will ever get. No late delivery truck arrives later in cosmic history. It should be noted that these disks are not all created equal. Some are massive and rich in elements heavier than helium, what astronomers call metals. Others are thin, dusty wisps with very little solid material. This means a disk with more mass and more metals can build more and bigger planets, including giant worlds like Jupiter, while a low mass, metal-poor disk may struggle to assemble even a single small rocky planet that looks remotely Earth-like. In the hunt for alien life, that difference is huge. A metal-rich disk is full of silicates, iron, water ice, and carbon compounds, the ingredients for complex chemistry, and, eventually, atmospheres. A poor disk might manage a few asteroid-sized bodies, but no true planets. No stable Goldilocks zone worlds, and no long-term surface water. There is also brutal time pressure. Observations with telescopes like ALMA show that most disks around young stars vanish in just 3 to 5 million years. The gas is blown away by radiation and winds from the star, or stripped by nearby massive neighbors. So it's time to find out the truth about planet formation. If worlds do not grow fast enough before the disk disperses, they simply never form. The race is on from day one. Whether a star ends up with a rich planetary system or almost nothing comes down to this race between growth and destruction inside its disk. And that race is not fair. The star's mass, its radiation, its magnetic field, even whether it has a close stellar companion, all tilt the odds. Optimistically speaking, many stars still win. In the next section, we will see how different kinds of stars, from gentle red dwarfs to fierce giants, change the rules of this cosmic competition, and decide which systems might truly be habitable. Stellar types: why some stars are natural planet builders. So if the race to build planets is tilted, which stars are actually favored to win? To answer that, we need to sort the stellar cast into 3 main types: low-mass M-dwarfs, sun-like G-type stars, and the massive O and B stars that burn like cosmic blowtorches. Each of these lives a very different life. M-dwarfs are cool, dim, and incredibly long-lived. Our sun sits in the middle, with moderate luminosity and a lifetime of about 10 billion years. O and B stars, by contrast, are huge, blindingly bright, and short-lived, burning through their fuel in just a few million years. This means their disks, their radiation, and their ability to host a stable planetary system all change dramatically with mass. Let's start with the sweet spot: sun-like stars. Around these, protoplanetary disks are usually massive enough to build both rocky worlds and giant planets like Jupiter. There is enough solid material to assemble Earth-like planets in the inner orbits, while farther out, icy cores can grow quickly and capture gas. The disk typically survives for a few million years, just long enough for these worlds to finish forming before the gas is blown away, and then the star itself remains steady for billions of years, giving any potentially habitable planet time to cool, form an atmosphere, and maybe, just maybe, develop life. But while sun-like stars seem ideal, they are not the most common. That honor goes to the M-dwarfs, the red dwarf stars. In the hunt for alien life, this matters, because most stars in the Milky Way are in this low-mass category. Kepler and systems like TRAPPIST-1 have shown that M-dwarfs can host many small, tightly packed planets, often in or near the Goldilocks zone. At first glance, that looks like a jackpot. pattern interrupt, there is a catch. M-dwarfs start their lives violently. Their strong magnetic fields drive intense flares and high-energy radiation that can erode protoplanetary disks and later strip atmospheres from close-in planets. It should be noted that their habitable zones lie very close to the star, where this radiation is strongest. So, while small planets are common, whether those worlds can keep thick, protective atmospheres is an open question. At the other extreme, massive O and B stars hardly give planets any chance at all. Their ultraviolet radiation and fierce stellar winds can blast away nearby disks in under 1 million years, truncating or completely dispersing the material needed to build planets. Even if some planets do assemble, the star's short life ends in a supernova before complex life has time to emerge. So it's time to find out the truth. Many of these giants may die surrounded by debris, not mature planetary systems. Exoplanet surveys back up this picture. Small planets show up frequently around both M-dwarfs and Sun-like stars, but giant planets appear far more often around more massive, metal-rich stars. This means the star's mass and composition pre-bias the outcome, deciding whether a system is filled with Earth-sized worlds, swollen gas giants, or almost nothing at all. In the next section, we will see how these stellar preferences shape the actual architectures of planetary systems, and why some end up looking nothing like our own. The invisible architect, protoplanetary disks and their deadlines. So, if the star's mass and metals, load the dice. What actually builds the planets we see? For that, we have to look at something we almost never see directly with our own eyes: the disk. Around a newborn star, the disk is the invisible architect. It should be noted that this architect does not use blueprints, it uses physics, dust, and time. And thanks to ALMA, the Atacama Large Millimeter/Submillimeter Array, we can finally watch it at work. When ALMA stares at young stars, it does not see one tidy pattern, it sees a zoo. Some disks are huge, bright, and carved into spectacular rings and gaps. Those gaps are not just pretty, they are smoking gun signs that young planets are already orbiting there, scooping up material and reshaping the system around them. But while some stars have these grand, planet-building construction sites, others sit inside faint, small, or already ragged disks that look like they are running out of material and out of time. In the hunt for alien life, that difference is absolutely crucial. So, let's begin with mass. Astronomers talk about the minimum mass solar nebula, the least massive disk that could plausibly have built our own solar system. The answer is surprisingly high, a few percent of the star's mass. This means a sun-like star would have needed a disk containing several tens of Jupiter masses of gas and dust. Yet when ALMA weighs real disks, many fall well below this threshold. Those lightweight disks might only manage a couple of small rocky planets, or a sprinkling of Mars-sized worlds, or in extreme cases, almost nothing at all. Disk lifetime sets the second deadline. Typical disks disperse in just 3 to 5 million years. If solid cores and planetesimals have not formed by then, the gas vanishes, and the chance to build giant planets evaporates with it, and environment can brutally shorten that clock. In dense clusters, nearby massive stars blast young disks with intense ultraviolet radiation, literally evaporating them from the outside in. In quieter regions, far from such giants, disks can linger longer, letting planets grow at a more leisurely pace. Inside the disk, the story is even more delicate. These disks are not just gas, they are filled with dust grains that collide, stick, and grow, from micron-sized specks, to pebbles, to boulders, to planetesimals, and finally, to planetary cores. But at every stage, growth can stall. Too much turbulence, and grains are smashed apart. Form cores too slowly, and rapid gas loss leaves them stranded as bare rocks. So it is time to find out the truth. A star does not simply get planets by default. It must be born with a sufficiently massive, long-lived disk in a relatively gentle neighborhood. Optimistically speaking, that combination is common, but not guaranteed. And as we will see next, when those conditions are met, the resulting planetary systems can look wildly different from our own. Radiation, magnetism, and stellar violence. How stars sabotage their own planets, but even when a star is born with the right disk, there is a twist. The very same star that nurtures its planets can also attack them. Young stars are not calm, gentle suns. They are hyperactive, violent objects, wrapped in magnetic fields and blasting out ultraviolet and X-ray radiation. They launch powerful stellar winds. They spin rapidly. All of this energy slams into the surrounding disk. It should be noted that this is not a subtle effect. High-energy photons heat the upper layers of the disk until the gas literally boils off into space. This process has a name: photoevaporation. Imagine the disk as a shallow, glowing atmosphere spread out in a flat plane. When the star's radiation hits it, the gas at the surface heats, expands, and reaches escape speed. Once it flows away, it does not come back. This means the clock for planet formation is not just set by how much material you start with, but by how fast the star is stripping it away. If the gas disappears too quickly, giant planet cores never grab enough hydrogen and helium to become Jupiters or Saturns. Even smaller worlds can be affected. In the hunt for alien life, that matters, because the amount of gas left over controls how much water and volatile material can be delivered to any future Earth-like planet in that system. On top of this, the star's magnetic field can literally reshape the inner disk. Close in, strong magnetic lines can grab material and funnel it along arcs, slamming it into the stellar surface in bright hotspots. The region where the field is strong enough to dominate the gas is magnetically truncated, carving out an inner hole. So, let's begin to think of it this way. The star is deciding where solid material can safely orbit. Move that boundary inward or outward, and you change where rocky planets can assemble, and how close anything can live to the future Goldilocks zone. In some systems we see warped, tilted inner disks, twisted by misaligned magnetic fields. Planets born in such environments may start life on inclined or eccentric orbits, or fail to form at all in the disrupted regions. And then there is the added chaos of having not one star but two. In close binary systems, where the companion orbits within about 50 astronomical units, gravity pulls on the disk like a tidal blade. The outer regions can be stripped away, the inner disk truncated, and any forming planets repeatedly destabilized. Observations show that such tight binaries are significantly less likely to host planets, especially wide, orderly systems like our own. So it is time to find out the truth. If stars can both build and destroy their planet-forming disks, what precise mix of stellar calm, disk mass, and quiet neighborhood does it take to reliably assemble worlds? And did our sun simply get lucky? Or are we seeing one path among many in a much larger cosmic experiment, the exoplanet census? How common are planetary systems really? If stars can both nurture and destroy their disks, what does the cosmic scoreboard actually look like? Are planetary systems rare jewels in the universe, or are we the ones who are unusual for even asking the question? To answer that, we have to step back and look at the exoplanet census. Kepler, TESS, radial velocity instruments, and even microlensing surveys have been quietly counting worlds for more than 2 decades, and the verdict is surprisingly bold. Around Sun-like stars, small planets between Earth and Neptune in size are not exotic at all. They are the default. Kepler's data show that if you pick a random Sun-like star, the odds are very good that it hosts at least one such planet, often several, packed into orbits far tighter than those in our own system. This means the early idea that our wide, orderly solar system represented some common template was simply wrong. Many stars cram multiple planets inside the orbit of Mercury, forming compact, clockwork systems that would have seemed impossible before Kepler. In the hunt for alien life, that is both exciting and a little disorienting. Our version of normal is clearly just one option among many, but while Sun-like stars are generous, the real overachievers might be the small red dwarfs. TESS and Kepler have shown that M dwarfs frequently host chains of close-in, Earth-sized planets. TRAPPIST-1 is the poster child. 7 Earth-like worlds, all squeezed well inside the orbit of Mercury, all tidally locked to a cool, red dwarf star. It should be noted that this tells us something fundamental. Even low-mass stars with modest disks can be extremely efficient planet builders when those disks survive long enough. Then there is the metallicity story. Radial velocity surveys reveal a sharp pattern. Giant planets are dramatically more common around metal-rich stars, those with more elements heavier than helium. Give a disk extra heavy elements, and you boost the odds of building massive solid cores that can grab thick atmospheres and become Jupiter, like giants. Take those metals away, and giants nearly vanish, leaving behind mostly small, rocky, or icy planets, if anything forms at all. So what about the stubbornly quiet stars, the ones that seem planetless? Even after we correct for detection biases and missed small planets, a real fraction of stars show no detectable worlds. Close binary systems, where a second star disrupts the disk, and low metallicity stars, where building blocks are scarce, stand out as particularly barren. Optimistically speaking, they are reminders that planets are common, not guaranteed. So it's time to find out the truth. Our galaxy is a patchwork of prolific planet factories and quiet, nearly empty systems, and mapping that pattern is the next clue to where habitable worlds, and perhaps life itself, are most likely to emerge. 2 stars, 1 cloud, a cosmic A/B test. So, what does this patchwork actually look like, up close? Let's shrink ourselves down, in imagination at least, and drop into a single giant cloud of gas and dust where new stars are being born right now. Inside this cold, collapsed collapsing cloud, a dense knot of material begins to fragment. One fragment splits in two. We get a pair of almost identical dense cores, side by side, falling inward under gravity. Same cloud, same time, nearly the same mass. They are cosmic twins, destined to become two sibling stars in the same system. On paper, we would expect them to live similar lives, but while they start almost the same, tiny differences creep in. One core spins just a little faster, carrying slightly more angular momentum. It sweeps up a touch more metal-rich dust, the heavy elements that planets are built from. Its local environment is shielded from the harshest radiation in the cloud. The other core is just slightly slower, slightly poorer in solids, slightly more exposed. This means that when both newborn stars ignite, their surrounding disks are not equal. Around the lucky star, the disk is thick, cool, and massive. Gas and dust circle in a broad, shadowed plane. Dust grains collide and stick, growing from smoke-sized particles into pebbles, then boulders. Within a million years, clumps of rock, planetesimals, begin to carve gaps and rings as they orbit. Give this disk a bit more time, and it becomes a full, planetary construction site. Multiple rocky worlds assemble in the inner regions, some Earth-like in size. Farther out, icy cores capture the remaining gas, inflating into mini Neptunes before the disk fades. In the hunt for alien life, this is the kind of system we dream about. Stable orbits, long-lived material, and a real chance to land in the Goldilocks zone. Now we turn to the twin. Its disk starts out lighter, more tenuous. A nearby massive star floods the region with energetic light. Photoevaporation, radiation literally blowing material away, strips gas from the outer parts before large cores can form. Dust grains struggle to grow, collisions shatter more than they build. Instead of planets, the star is left with a thin, ragged belt of debris, or, from our perspective, nothing at all. It should be noted that both stars shared the same birth cloud. The difference came from those tiny initial imbalances, amplified over just a few million years. Optimistically speaking, that means nature does not need dramatic changes to tip a star from planet rich to planet poor. So, let's begin to compare this thought experiment with reality. Alma's sharp radio eyes and Dwest's infrared vision now see exactly this diversity in young clusters, one star with a bright, structured disk right next to another that is almost bare. So it's time to find out the truth, which side was our sun on, and what invisible dice were rolled before Earth ever had a chance to exist. Dwest and Alma, watching planets being born in real time. To answer that, we need to actually watch planets being born. Not in an animation, not in a simulation, but in real telescopes, staring at real baby stars. So, let's begin with Alma, the Atacama Large Millimeter/Submillimeter Array. This is not one telescope, but dozens of radio dishes spread across the high Chilean desert, all working together as one enormous eye. At the long wavelengths Alma uses, cold dust and gas in a protoplanetary disk shine brilliantly. Structures that were once just fuzzy blobs suddenly become sharp rings, carved gaps, and lopsided clumps. What could sculpt those patterns? In the hunt for alien life, those gaps are smoking guns for forming planets quietly orbiting, sweeping material out of their paths. One famous example is the atrial Tau system. Alma revealed a young star wrapped in a disk with multiple bright and dark rings, like grooves on a record. The star is only about 1 million years old, yet the architecture already looks like a planetary system under construction. This means that by the time a star is barely out of its cosmic infancy, the question of planet rich or planet poor may already be decided. But while Alma shows us the bulk structure and mass of these disks, we also want to know what they are made of. Are we looking at a future desert of rocks, or a system rich in water and organics? That is where the James Webb Space Telescope comes in. Dwest is an infrared powerhouse. Its mirrors and instruments are tuned to see warm dust and glowing gas hidden inside the dusty birthplaces of stars. It measures the fingerprints of molecules in the disk, water vapor, carbon dioxide, methane, and complex organic compounds that one day might help build habitable, Earth-like worlds. Together, Alma and Dwest act like forensic tools at a cosmic crime scene. Alma sketches the outline, how massive the disk is, how far it spreads, where the rings and gaps lie. Dwest fills in the chemistry, whether there is enough water for oceans, enough carbon for atmospheres, and enough solid material in the Goldilocks zone to assemble rocky planets. It should be noted that when both instruments agree on a massive, structured, chemically rich disk, the odds strongly favor a busy planetary system in the making. And when they do not, when Alma sees only a thin, dispersed first haze, and Joest finds little warm dust or gas, the verdict is harsh. That young star is likely doomed to remain planet-poor, maybe even planetless, in a universe where its neighbors thrive. Optimistically speaking, we can now start turning these disk snapshots into a rule of thumb. In the next segments, we will connect a star's type, metallicity, and environment to what Alma and Dress see, and finally ask, given a particular star, what kind of planets, if any, should we expect at all? Binary or solo? How stellar companions steal planets, so if disks write the first draft of a planetary system, there is another question we have to ask. What happens when a star has to share that disk with a neighbor? Most of us picture a star as a solo act, like the sun, but while that is true for our own system, it is not the rule of the universe. It should be noted that many stars are born in binary or even triple systems, bound together in a complex gravitational dance, and in that dance, the distance between partners is everything. Wide pairs, separated by hundreds of astronomical units, can each hold on to their own disks. Both stars can, in principle, grow planets in peace. But when two stars are packed closer than about 50 astronomical units, the story changes dramatically. Their gravity pulls hard on any disk trying to orbit just one of them. The outer regions, where icy material and giant planets would normally form, are sheared off or simply never settle. This means the disk becomes smaller, lighter, and far more chaotic. Planetesimals that should quietly merge into worlds are instead stirred, scattered, or even ejected from the system entirely. In the hunt for alien life, this is a problem. You cannot have a habitable, Earth-like planet without first surviving this early gravitational crossfire. Observations back this up. When we look at close binaries with separations under that SEER 50 AU threshold, they are significantly less likely to host detected planets than single stars or wide binaries. The same kind of star, the same age, the same broader environment, but one has a clingy stellar companion. Suddenly, the odds of building a stable planetary system drop. Here is the pattern interrupt. Two stars, born from the same collapsing cloud, with almost identical initial conditions. Alma zooms in. Around one, we see a bright, massive disk with clear rings and gaps, a textbook planet factory. Around the other, in the very same system, there is only a tiny, faint disk, or nothing at all. One star has material to build a rich family of worlds. The other lost the planet-forming lottery before it ever began. So it's time to find out the truth about planetless stars. Often, the right question is not, why does this star have no planets, but what happened to its disk? A close, disruptive companion can strip, truncate, or destabilize that disk in just a few million years, long before planets can assemble. Optimistically speaking, this gives us a clear rule. If we know a star's companions and their orbits, we can start predicting whether a disk ever had a fair chance. In the next section, we will connect that idea to stellar mass and type and ask which kinds of stars are most likely to keep their disks long enough to grow truly habitable worlds, metal-rich suns, and metal-poor orphans. Chemistry is destiny, so if disk lifetime sets the deadline. What decides how fast planets can actually be built before the clock runs out? Two stars can keep their disks for the same few million years, yet one ends up with a majestic planetary system, while the other is almost bare. To understand that, we have to talk about chemistry. In astronomy, metallicity has a very specific meaning. It is not just iron or shiny metals, it is everything heavier than helium, carbon, oxygen, silicon, magnesium, iron, and more. All of those elements were forged in previous generations of stars and scattered into space by supernovae and stellar winds. So, let's begin with this picture. Every new star is a chemical inheritance from the dead stars that came before. This means a metal-rich star forms from gas that has been recycled many times. Its disk contains more dust and rock, more solid grains that can collide and stick, building the seeds of planets. A metal-poor star, by contrast, is like a construction site short on bricks. There is still hydrogen and helium gas everywhere, but far fewer solid pieces to assemble into worlds. It should be noted that when we look at the data from exoplanet surveys, this chemical difference shows up very clearly. Giant planets, the Jupiter and Saturn analogs, are strongly biased toward metal-rich stars. Around stars with high metallicity, we see massive planets in close orbit and at wider distances. Around metal-poor stars, they almost vanish. The best explanation is that only disks with enough heavy elements can quickly build a solid core 10 or so times Earth's mass before the surrounding gas disperses. Miss that window, and the planet stays small forever. But while giant planets are picky, small rocky planets are more forgiving. We now know that Earth-sized and super-Earth planets appear around a wide range of metallicities, especially around red dwarf stars. Even a modest amount of dust can, in principle, be spread out into many compact, rocky worlds. In the hunt for alien life, that is encouraging because it suggests that truly Earth-like planets do not require an extremely metal-rich environment. However, there is a limit. At very low metallicity, there may simply not be enough solid material to assemble many Earth-mass planets at all. A star can keep its disk, but if that disk is chemically primitive, it may form only a few small bodies, or none large enough to hold a substantial atmosphere or stay habitable for long. So it's time to find out the truth about how hidden this effect really is. Two stars can look almost identical in brightness and color, yet their internal chemistry quietly decides their fate. One might host a TRAPPIST-1-like chain of tightly packed rocky planets. Another could support an HR 8799 style system of massive giants. A third might end up almost empty. And as we will see next, once you combine this chemical lottery with stellar mass and type, the odds of building life-friendly systems change in a very surprising way. Are planetless stars truly empty, or just hiding tiny worlds? So here's the uncomfortable question. When we say a star has no planets, do we really mean empty, or just empty to our limited eyes? In the hunt for alien life, this detail matters a lot, because our main tools for finding planets are extremely biased. They love big, close-in worlds, and mostly ignore everything else. This means that when a survey labels a star as planetless, what it often really means is, we did not see any large planets on tight orbits. That is not the same as saying there are no Mars-sized, Moon-sized, or even asteroid-sized worlds quietly circling far away. Take the transit method. A planet has to pass directly in front of its star from our point of view, dimming the light by a tiny amount. For a Sun-like star, an Earth-sized planet blocks less than 1 part in 10,000. Around a noisy, variable red dwarf, that signal can drown in the star's natural flickering. And if the planet is smaller than Earth, or orbits farther out than the Goldilocks zone, the dip becomes so slight and so rare that for many targets, we simply cannot detect it. The radial velocity method is no kinder to small worlds. Instead of watching a shadow, we watch the star wobble in its orbit around the system's center of mass. Big planets close in tug hard, tiny planets far out tug softly. Below a certain mass, the wobble is smaller than the jitter from the star's own turbulent surface. It should be noted that for a large fraction of stars, we can only rule out planets above a certain mass within a certain distance. Everything smaller or colder remains invisible in the current data. Then there is microlensing, which briefly brightens a background star when a foreground object's gravity acts like a lens. Microlensing has revealed something startling: a population of free-floating planets drifting through the galaxy with no star at all. Some of these lonely worlds were probably born in a system and then violently ejected by gravitational encounters. So it's time to find out the truth. A star we see as bare today might once have had a full planetary system and lost almost everything. This leads to a subtle but crucial point. When astronomers talk about planet occurrence rates, they usually mean planets above a given size, in specific orbits, over a limited observing time. The true fraction of stars with any planets at all the way down to rubble-sized bodies, is still unknown. Optimistically speaking, disks seem so common that true cosmic loners may be rare, but we cannot yet prove it. So, let's begin to refine our central question. Given everything we now know about disks, stellar types, metallicity, and companions, how typical is our Sun, really? And how many stars in the universe never had a real chance to build planets, let alone habitable, Earth-like worlds? In the next section, we will push as close as current evidence allows, putting it together, a simple map of which stars get planets. So, let's begin to turn all of this into something we can actually use. If you look up at a random star, how do we guess whether it has planets, and what kind they might be? In the hunt for alien life, astronomers have converged on a simple mental checklist. 4 big levers tilt the odds of planet formation: the type of star, its metallicity, whether it has close stellar companions, and the kind of environment it was born in. Each one nudges a system toward rich planetary architecture, or toward cosmic emptiness. First, star type. More massive, hotter stars have intense radiation and short lifetimes, which can blow away disks quickly. Very low-mass red dwarfs have gentler light, but also smaller, lighter disks. Sun-like and modest red dwarf stars sit in a kind of sweet spot, long-lived, not too violent, with disks that can be just massive enough to build both rocky and giant planets. Second, metallicity. This means how much stuff heavier than hydrogen and helium the star contains. It should be noted that metals are the raw solids that seed dust grains, planetesimals, and eventually planets. High metallicity boosts the solid content of the disk. speeding up the growth of planetary cores before the gas disappears. Third, close companions. A nearby second star can truncate or tilt the disk, stir it gravitationally, and even eject growing worlds. Systems with separations under a few dozen astronomical units are especially harsh. Finally, Earth environment matters. Calm regions let disks survive for millions of years, while crowded clusters with strong radiation and close flybys can strip disks early. So, put these levers together. Imagine a single, sun-like, metal-rich star, no close companion, forming in a relatively quiet part of a molecular cloud. Its disk is reasonably massive and lives for 3 to 5 million years. In that time, rocky planets assemble in the inner region, while icy cores further out grab gas to become giants. The result? A high likelihood of a multi-planet system with several small rocky worlds, maybe a couple of gas or ice giants, and a decent chance that at least one planet sits in a Goldilocks zone. Now pattern interrupt. Take almost the opposite case. Picture a low metallicity M dwarf locked in a tight binary inside a crowded cluster. The disk starts out light, is shredded at the edges by the companion, and is eroded by nearby massive stars. Disk lifetimes shrink, core growth slows, and the result may be no planets at all, or at best a few small rocky worlds hugging the star with little prospect for thick atmospheres or habitable conditions. So it's time to find out the truth from the data. Kepler and other surveys suggest that for single sun-like stars and single M dwarfs with decent metallicity, the majority host at least one small planet. But while these stars are rich, tight binaries and very metal-poor stars show significantly reduced planet occurrence rates. Optimistically speaking, this gives us a probabilistic map, not a guarantee. Individual stars can surprise us, but on average, some regions of the galaxy and some kinds of stars are simply more likely to host planets. Next, we will ask how this map lines up with the places most likely to host truly Earth-like, habitable worlds. So, did we win the cosmic lottery, or just play the odds? So, if we now have this probabilistic map of where planets are most likely to form, where does that leave us? Did our solar system beat impossible odds? Or did we simply sit down at a table where the dice were already a little loaded in our favor? To answer that, we need to retrace the chain we have been building. Stars and planets are born together, out of the same collapsing clouds of gas and dust. The newborn star ends up in the center. The leftover material flattens into a rotating disk. Inside that disk, dust grains collide, stick, and slowly assemble into planet cores, while gas flows, freezes, or escapes. But while this sounds almost automatic, it should be noted that the disk itself is the real gatekeeper. Disk mass and lifetime are crucial. If the disk is too light, there simply is not enough raw material to build many planets, especially giant ones. If the disk is stripped by radiation, or blown apart by nearby massive stars, or drained by magnetic winds in just a couple of million years, the assembly line shuts down early. Companions do not help either. A close binary star can shear off the outer disk, tilt orbits, and fling forming worlds into unstable paths. So, planet formation is natural physics, but it is also a race against time and disruption. On top of this, the type and composition of the star bias the outcome. Small red dwarf stars tend to keep their disks longer, favoring lots of small, tightly packed planets. Sun-like stars sit in a sweet spot, with enough mass and metals to build diverse systems, from hot super-Earths to distant icy giants. Very massive stars burn bright and fast, blasting away disks before many planets can finish forming. Metal-rich stars offer more solid building blocks. Metal-poor stars are working with a nearly empty toolbox. So where does our sun fall in all this? As a single, moderately metal-rich, sun-like star in a relatively calm neighborhood, it occupies a high probability category. This means that forming multiple planets, including some in the Goldilocks zone, was not a miraculous jackpot. In the hunt for alien life, our situation looks less like a winning lottery ticket and more like the expected outcome of decent starting conditions, plus a few lucky breaks, such as no nearby supernova and no close stellar companion. If stars like this are common, what does that say about habitable worlds? Kepler and other surveys already suggest that small planets are abundant around both sun-like stars and red dwarfs. Even if only a fraction land in the habitable zone, and only some keep a stable atmosphere, the numbers add up quickly. Across the Milky Way, we are likely talking about billions of potentially Earth-like, life-friendly planets, yet there are still big uncertainties. How many disks fail completely before planets grow? How many small planets are hiding just beyond our current detection limits? How often are young planets later destroyed, thrown into the star, or ejected into interstellar space? So it's time to find out the truth with better data, but the trend already points one way. Planets are a common, though not guaranteed, outcome of star formation. Optimistically speaking, our existence looks like common physics, playing out under slightly fortunate circumstances. Every apparently empty star we see is a quiet reminder of how many steps had to line up just right for a system like ours to exist at all. But there is one more question we have not tackled yet. Among all these worlds, how many could actually host life that looks anything like us? Your turn to choose a star, CTA, and next questions. So let's turn that big question back to you. If you had to place a quiet bet on the cosmos, which kind of star would you choose as your best hope for life? Close your eyes for a second and pick one in your mind. A tiny red dwarf, cool and long-lived, with its Goldilocks zone pressed in tight, a sun-like twin with wide, slow orbits and room for a spacious planetary system, or a massive blue giant, blazing bright and burning through its fuel in a cosmic instant, using the framework we have just built together. What do you think the odds are that your chosen star actually gets planets, and what those planets look like? In the hunt for alien life, this is no longer an abstract game. We know that most red dwarfs carry small, close-in planets. We know that sun-like stars often wear systems that, at least in outline, resemble our own. Massive blue stars, by contrast, tend to blast their disks apart before many worlds can fully grow. So, based on that, did you pick the careful favorite or the dramatic long shot? Tell us in the comments which type of star you now think is the best bet for a truly habitable, Earth-like world. And then, make it personal. If you had to live there, would you rather move into a compact, TRAPPIST-1 style system, where planets share week-long years and other worlds loom huge in the sky? Or would you choose a wide, airy solar system analog, with long seasons, big orbital real estate, and more elbow room between worlds? It should be noted that neither choice is obviously safer. Tidal locking near a red dwarf brings its own climate puzzles. Distant orbits around a brighter star can mean colder, thinner atmospheres, so it's time to find out the truth about your own instincts. Which cosmic neighborhood feels more like home to you, and why? If you want to go deeper, we have linked a follow-up playlist that dives into specific systems. TRAPPIST-1, with its chain of resonant orbits, HR 8799, where giant planets sketch glowing arcs through a young debris disk, and new James Webb Space Telescope observations that are starting to read the atmospheres of known exoplanets, searching for water vapor, clouds, and, one day, possible biosignatures. Optimistically speaking, each of these targets is another test of the ideas we have explored here. This means the story is only just beginning. If you subscribe and stay with us for the next episodes, we will ask how often these planets manage to keep their atmospheres at all, how stable their climates really are over billions of years, and what it would actually take to detect life across interstellar distances. How many signals would we miss? How many would be impossible to ignore? The next time you step outside at night and look up, try a different question. Do not just count how many stars you see. Ask instead, which of those stars ever had a disk heavy enough to build worlds, which still cradle planets in silent orbit, and which never got the chance to make a single place where life could try to begin?